Thank you very much. Everybody got the coffee? I need my coffee. No alcohol yet. Thank you for coming and braving this kind of sultry weather. Hopefully this image of daybreak looking off the east coast of Madagascar will buoy your spirits for sun. So my task in the next hour or so is to summarize 32 years of research. And that's kind of a daunting task, but I'm going to try to do my best at it, not only about scientific discovery, but about how that led us into other aspects of life that we didn't expect. And that's kind of towards the end of the talk. So let's begin. I will assume, rightly or wrongly, that many of you don't know much about Madagascar. I confess, before I went there, I knew very little about the country. I knew about the animals, and that's what intrigued me to go to Madagascar, but I knew very little about the country. So let's start here. Many people's exposure to Madagascar is through these movies, this series of 3 movies, and I will actually have a quiz question for you at the end of the talk about these movies. But I want to give you a little background about Madagascar. First of all, everyone knows that it's off the southeast coast of Africa, but very few people know how big it is. And in fact, if I give you a quiz question and ask you how big it is relative to Colorado, many of you would say about the same size. Most of you would probably say smaller, but it's actually more than 2 times the size of Colorado. So it's about 1,000 miles from north to south. It's a huge island with tremendous topography on it. And it's home to about 32.5 million people. And to put that in context, that's Colorado has what, about 6 million people. This population is about equivalent to that in the Ukraine or Peru. It's more than all of the people in Australia. And in many ways, they're amongst the most destitute and forgotten people in the world. And that particularly pertains to people who live in the countryside. And obviously, as a paleontologist, we work in the countryside. Madagascar is also known as the Great Red Island, and that's primarily because much of it is composed of these iron-rich lateritic soils that are bleeding out into the Mozambique Channel here because of deforestation. So one of the first bits of knowledge about Madagascar came about because of this French naturalist, primarily a botanist by the name of Commerson. And he is famous for having this quote: "Madagascar is the naturalist's promised land. There you meet bizarre and marvelous forms at every step." And boy, was he right. For the plants that he studied, he was amazed to see that there were this great variety, and probably the signature plants are these baobab trees like these. They're called upside down trees because it looks like the roots are sticking up. And in fact, there's about 11 or 12,000 species of plants in Madagascar, 84% of which are endemic. In other words, they're found nowhere else in the world, only found in Madagascar. I, of course, as a vertebrate paleontologist, and that's my title here, I'm a curator of vertebrate paleontology. I've been here for almost 10 years. And before that, I had a career as a professor at a college back east for 34 years. But here I am, loving my job. And these are the extant, backboned terrestrial vertebrates that live on Madagascar today. And there's a lot of weird animals. I'm talking about aliens that Maria was talking about. Here's a tomato frog, plowshare tortoise, a leaf-nosed snake, tenrec, these chameleons. This actually is a fully grown adult chameleon, arguably the smallest reptile in the world. And these are the signature animals of Madagascar, right? The lemurs. So here we have a black and white ruffed lemur, and there we have an eye. Of these, the level of endemism, in other words, the level of being unique to Madagascar, is really high. It's about 98%. And if we look back in the very recent fossil record, only going back a few thousand years, things get even weirder. There's not just lemurs, there's giant lemurs. So these are reconstructions of giant lemurs that lived Again, only a few thousand years ago. This one here is about the size of a gorilla. And for context, here is the largest living lemur living today. And not only that, there were things like pygmy hippos, this one over here. And actually there are some villagers in the area that claim that they've seen this as recently as 1976. But there's a common hippo from which it may or may not have been descended. And then it gets even weirder because Madagascar is home to a fossil or subfossil elephant bird, a ratite, a flightless bird. And this animal is huge. It's about 880 pounds, which is almost 3 times the size of the largest living ratite today, and certainly much larger than a chicken. And if we put that in the context of eggs, here are the eggs. Here's a chicken egg, ostrich egg, and apiornis, and it gets even more ridiculous. Here is a hummingbird egg. And so this is about 20 pounds. This is about 1/3 of a gram. So a great diversity in egg sizes there. And then it gets even weirder because in 2018, this elephant bird was described. And this one is almost twice as big as apiornis, that other elephant bird. And so here we are at about 10 feet tall, almost 10 feet tall, and almost twice as heavy as that elephant bird that I showed a picture of before. And so as we're moving towards Thanksgiving, just think of what that might mean, right? Wouldn't you love having an 80-pound drumstick to serve? Anyway, kidding aside, what I knew about Madagascar and its unique fauna and flora was intriguing to me. And so I wondered, where did those animals come from? They're unique to Madagascar. When did they get there and from where did they come? All of those kinds of questions. And actually in 1993, which is when I started this project, this was touted in the literature as the greatest unsolved mystery of natural history. So as a paleontologist, I thought, well, okay, I can go back in the fossil record and maybe I can find some proto-lemurs or proto-tenrecs or proto-tomato frogs or whatever. And so this is the geological time scale, which we all have to deal with over here is in millions of years. Unfortunately, for me at least, this whole interval of time, the Cenozoic, is almost completely devoid of continental rocks. And so if I want to look for terrestrial vertebrate animals, this is not the time to be looking in. So the next best opportunity is to look in the late Cretaceous. And here there are rocks of appropriate age and appropriate type. In other words, they're continental rocks. And so that's what we set our sights on. So here, just to give the temporal context, again, here's the geological scale. You can't see these numbers here, but it goes from 0 down to 180 million years ago. And up here, only back to about 87,000 years, not million, 87,000 years is when we have these subfossil lemurs and the hippos and the elephant birds and so on and so forth. The only other fossil record of mammals is way down here at about 165 million years ago, and it's based on this tiny little jaw with 3 teeth that doesn't have any relationship whatsoever to the modern fauna. There's no way that this thing, in fact, there's huge arguments about whether this is potentially even a monotreme as opposed to a therian mammal, in other words, marsupials and placentals. So we have a gap of about 165 million years to fill, and we know, based on what I said before, there's no tertiary non-marine rocks for me to look in to find proto-lemurs, proto-tenrecs. But there is the late Cretaceous. And why did we zero in on this? Because we thought we had a chance. And so I have to do a little history here and go back to 1895. 1895 is when the French army invaded Madagascar and made it a colony. Madagascar has been independent since 1960. But this was the conquering army. They landed close to, up in the northwest, in fact, very close to our field area. And in many of these early armies, the colonizing armies, they would appoint certain soldiers that had scientific interest to collect stuff. And it could have been birds, it could have been mammals, it could have been rocks, it could have been fossils. And this fellow, Adjutant Landillon, which basically means Sergeant Major Landillon, found a bunch of rocks, but he also found these. And he recognized them as fossils, and he sent them back to the reigning French paleontologist at the time, Charles Desparet. And this is an aside, but does he remind you of anybody? To me, he reminds me of Inspector Clouseau. Anyway, Desparet wrote this paper in 1896, the year after the conquering army invaded Madagascar, and I was aware of this paper. I was also aware of the fact that other paleontologists had gone to Madagascar since 1896. Anyway, this is a map from 1895 where we know that the French army landed right about there and then made their way to the capital city. It was an army of about 20,000. They lost about 6,000 to malaria and other disease and very few to actually armed conflict. But they landed close to a village called Bereeft, and since then a number of expeditions have gone to Madagascar, and in fact to that very same place. So the French went there several times, Japanese, Italians, and then joint French Malagasy expeditions. These all lead up to 1989. And through all of those expeditions, they didn't find much. And I invite you to ask me at the end why they didn't find much, because I'm going to show you that we found a lot. And I'm not going on an ego trip there. There's a very good reason for the fact that we found a lot and they didn't. But the point is, they just found fragments. They found teeth and parts of bones. Here are a couple of vertebrae. There's part of a claw, a dinosaur claw. But they found no articulated specimens, no two bones that went together. So in July of 1993, I started this project. And again, knowing very little about the country, I knew that we had to fly to the capital city because that's where the main airport was. But I didn't know that you couldn't go up to the Hertz rent-a-car desk and rent a couple of vehicles. And so it took us about 3 weeks to find 3 vehicles. None of them were younger than 30 years old. One of them had been converted into a chicken coop. But when they found out that we had a little bit of money, they put an engine in it, put some wheels on it, some seats in, and away we went. And so here it was. So the distance from about here to Grand Junction, about 240 miles, took us 2.5 days because of the state of the vehicles and because of the state of the roads. So that began what we call the start of the Majunga Basin Project. This is the Majunga Basin, the depositional geological basin in which we've been working. We've now had about 14 expeditions that have gone to that area of the country. And this is what it looks like. And if you're used to the Badlands of South Dakota or the Hell Creek Formation in North Dakota or Montana, this doesn't look very promising, but I can assure you that every one of these areas that has exposed rock is filled with fossils. They're all over the place. It's an incredibly rich area. And we've done the geology on it, and we know really well now what the geology looks like. I don't want you to get buried in this stuff, but we focused on this 10-meter interval called the Anemba-Lemba member because it represents a depositional environment that preserves fossils very, very well. And this further documents that we've got the geology really figured out. Again, this is the Majunga Basin here, and here it's enlarged. We've been working in this Maveron Formation, and now we have 4 major field areas. And what do? We go out and we prospect, especially in the early years. We went out and prospected. It means you walk into any area of exposed outcrop, get down on the ground and look for fossils, and again, we found a lot. And in areas where they're richly concentrated, we dug these massive holes in the ground. You can get a sense of the size here. You can't get a sense of the hardness of the rock or the fact that we don't have any access to mechanized equipment. So all of this is done by hand. And here's an area that's exposed. We're exposing a bunch of bones here and down here, taking the loot. In other words, putting dinosaur and other bones into plaster jackets. And we are not dinosaur headhunters. We want to know the paleoecology of the entire fauna, and so we collect everything. And so we do things like screen wash, and we do dry screening as well to pick up the very tiny things, fish teeth, fish vertebrae, mammal teeth, and so on. So the sum total of our work over 14 years is that we have about 25,000 specimens, all of which are downstairs in B2, part of the Avenir Collection Center. We've described 23 new genera, 24 new species. We actually have quite a few more to describe. We're waiting for still better specimens before we do that, or we're waiting for the research to be done. This is a long process. But almost everything that we find, because it's in the southern part of the world that has not been explored very much, is new to science. And I'm actually going to do a few tangents here and there to talk about how we named these animals. And here's a bunch of bragging, but I do it on behalf of my colleagues. We published a lot of scientific papers on that. It's involved 160 authors, many of them world experts from around the world. More than 50 of them are graduates or undergraduate students, so it served as a good training ground for students. And 7 master's theses and 10 Ph.D. dissertations, evenly distributed roughly between the USA and Madagascar. And specimens have been displayed in 45 museums and other institutions worldwide. So that's a whole lot of bragging, but there's 2 points I want to make there. One is that I've had a lot of wonderful colleagues working on this material. I'm up here as one person, but this has not been a one-man show. And the other is the very, very good fortune that we had in finding spectacular material. And here it is. These are reconstructions of the many animals, again, new to science, that we've found. Everything from big old dinosaurs to turtles to birds, mammals, frogs, and so on and so forth. The point I want to emphasize with the next slide is that these aren't represented by just a fragment of bone here or a tooth there and then an artist reconstructs them. They're actually based on entire skulls and skeletons that are exquisitely preserved. Again, this is part of the good fortune that we've had in coming across this area that had not been excavated in the way that we did. And so here are just some examples. I'm going to run through a few of these, not all of them, because we don't have time, but here's 4 different kinds of crocodiles. Here's a really big frog, 2 kinds of mammals, and dinosaurs. And so I'm going to go through them. But bear in mind that this is not all that we found. We have found just little bits and pieces of things too. So we have thousands of fish vertebrae, for instance, but even these are informative, and we're just starting to unravel that story. But basically the story is that we've discovered a time in which a lot of marine species are becoming freshwater. In other words, they're transitioning to the freshwater of Madagascar. But going to the more the more complete animals. So when we started this expedition, we found just little bits and pieces of bones of this animal, and we know enough anatomy, comparative anatomy, that we knew that it was a frog, and we knew that it was huge. Biggest, baddest frog that ever lived. Here is a reconstruction of it. This is the biggest frog that lives on Madagascar today, and there's a number 2 pencil. This is arguably the heaviest frog and almost undoubtedly the most vicious frog that ever lived. And because we recognized it was a frog, but we just had little bits and pieces of it, we just referred to it as the frog from hell, because it was big and bad. But then we incorporated that into a new generic name, Beelzebufo, because bufo means toad and Beelzebub is the devil, right? So we made this generic name. And here it is depicted in a National Geographic magazine. from, 2009. And behind here you can see some eggs, and here you can see a hatchling dinosaur, and here is a very unfortunate hatchling dinosaur. And so this concept has been repeated in several TV shows of showing Beelzebufo taking down dinosaurs, and I love that concept of them taking it down. We actually had a researcher who calculated or took bite force data from a modern relative. These are called Pac-Man toads in South America, and they're also quite vicious, but they're much, much smaller. And they did bite force, they used bite force transducers and figured out, calculated up using regressions, how strong the bite force of this animal was. I don't necessarily believe it, but they said that it's equivalent to that of a female lion or a female tiger. These were vicious animals, certainly more than a coyote and certainly more than a wolf. That's their calculations. So what does that all mean relative to the modern fodder? Remember that question I had, where did those animals come from living today? Well, the frog fauna in Madagascar is tremendously diverse. There's over 500 species, and this is Beelzebufo relative to those tiny little frogs. And in order to figure that out, how they're related, we have to do family trees, and that's essentially what this is, a very complicated one. But these are all the modern frogs. Every one of these is a modern frog from Madagascar. And so we're hoping, of course, that maybe we can see that Beelzebufo is sitting in one of these lineages that gave rise to one of these smaller frogs. Nope. It's way out, doing its own thing. It's way off the charts in terms of potential ancestry to any of these modern frogs. So Beelzebufo was not an ancestor to any of these modern frogs. Same thing with the snakes. I'm not going to go into etymologies here, but we have about 6 different kinds of snakes. This one is actually the largest Mesozoic snake known from anywhere in the world. It was about 8 meters long, and they belong to 2 different families. And if we do the same sort of thing and look at a phylogeny or a family tree and see whether or not any of our snakes are on any of these lineages, they're not. They're way out here. They have nothing to do with the direct ancestry of any of these modern animals. We also have about 5 or 6 different kinds of turtles. I'm not going to bore you with a family tree of these, but this is a remarkably well-preserved specimen. Here's the shell, there's the skull, and here it is reconstructed in water, eating tadpoles of Beelzebufo, actually. And we named it Sahunachiles. And that's because it has a big, wide mouth like a frog does. And we also know from its hyoid apparatus and a number of other features, including the long neck, has an incredibly long neck, that this was probably a gape and suction feeder. In other words, it would be in the water and open its mouth really quickly, and the prey items, whether they're fish or tadpoles or whatever, can get sucked in. And so that's not that unusual. That's what some turtles do. But this belongs to a whole big group of animals called paleontologist, and none of them do that. So this is the only paleontologist that does that, and it does it really, really well, or did it really well. And we know that from, again, the hyoid apparatus, the long neck, but also the shape of the skull. That's what's found in turtles and this other major group called cryptodires that have all of those features. We have 6 and probably 7, and 7 is news as of about 2 weeks ago, different kinds of crocodiles. And here are 4 of them that are already studied. The other 2 or 3 have not been named yet, but they're in the process of being described. And the scale bars are different here. So these 2 are really quite small, and these are really quite big. This one here, we have a mounted skeleton of sitting over here in a reconstruction there. I don't know if you can see it, but it's on the right-hand side on the stage here, and you're welcome to come up and look at all of these later on. I should have mentioned that my favorite animal is right here, Beelzebufo, and so you can get a sense of its size as well. in 3 dimensions rather than 2 dimensions. So of these crocodiles, they range in a whole a number of carnivorous adaptations, but here's one that is probably not a carnivore. This is something we call Simosuchus, and here's its chest region, its neck, the top of its skull, the side of its skull, side of its lower jaw, and here is the front of its skull. And there's an artist's reconstruction. But the really odd thing is that it doesn't look like any normal crocodile. We know it's a crocodile based on the morphology of the back of its skull. But the front of its skull is just not like a good card-carrying crocodile. A good card-carrying crocodile has got a long, skinny snout and conical teeth for catching prey. This thing has a pug-nosed snout, and its teeth look like this. Those kinds of teeth are found in modern-day iguanas that, of course, eat plants. And so we think this is actually a plant-eating crocodile and doesn't get much weirder than that. Of the dinosaurs, I'm just going to look at the theropod dinosaurs here, Majungasaurus, Mexicasaurus, and Rahunavis. And this is Majungasaurus. This is arguably our best-known animal. We have 5 or 6 or 7 skeletons of it, or partial skeletons. It's remarkably complete. And it's also, I mean, you'll hear me use this word bizarre or weird quite frequently. It is bizarre or weird because it has this funny bump on the top of its head, and it has these tiny little arms and hands. I mean, it's not even like Tyrannosaurus or Allosaurus. It doesn't even have claws. It's just got these little nubbiny fingers, and that's pretty weird. And then here is Mexicasaurus. Mexica means vicious in the Malagasy language, and saurus is a frequently used suffix for dinosaur names, and it means vicious lizard. This thing was about the size of a German Shepherd. It's sitting right here. Most of it is tail. It's got a very long tail. But it is also weird or bizarre because it has these teeth that point pretty much straight forward. No other dinosaur does that, and we have the complete skeleton of it. And so in terms of etymologies, one of the things I have to highlight here is that we named it Mexicasaurus for the genus name, but the species name we named Knopfleri. And why do we do that? We sit in the quarries, hot sun, hours, days, and we don't find anything. Graduate students ask me, can they play music? And I say, of course you can play music, but every once in a while, I got to play my music. And I happen to like this one singer, songwriter, guitarist, Mark Knopfler, very much. And it seemed like every time we found bones of Mexicasaurus, my music was playing. And so we decided to name it after Mark Knopfler. And the end result of that is that we got 7 free tickets to a concert at the Beacon Theater. And this skeleton is actually on display in a rock and roll museum in Scandinavia. Here's a much smaller dinosaur that we found. It's remarkably well preserved. We don't have all of it. We only have the parts shown in yellow here. Actually, we do have the lower jaw, which isn't shown in yellow. That was a later discovery. But here's the hind foot to give you a sense of the quality of preservation. And the quality of preservation is so good that we even found this whitish schmutz on the claw. And then we analyzed that. I didn't analyze it this way above my head to do that sort of thing. But we analyzed that, and it's actually beta keratin, which is the kind of keratin that's found in birds and reptiles. And then on the back end of the ulna, this bone right here, we found all of these bumps, and those are called quill knobs. And you see them in things like woodpeckers especially, but all birds with secondary flight feathers have them. And so that's how we know that this was a flying dinosaur. It's actually a very controversial specimen because depending on the month, there'll be a paper that comes out that says this is a bird-like dinosaur, and the next month it's a dinosaur-like bird. So it's right close to the boundary between the two. And because of this sickle-like claw, we actually named it Rahunavis, and that means bird menace from the clouds. This is another important bird specimen described by our director of Earth Sciences, Pat O'Connor, and several other authors. And this was significant in that this is about a crow-sized bird, so the skull is about that long. And here are the actual bones. We use micro-CT technology to deal with such small specimens. And so here are all the bones segmented out and then reconstructed digitally and then put together in an artist's illustration. The really weird thing about this is there's no bird in the Mesozoic that has a bill that is this deep. And there's no bird in the Mesozoic that has a bill made up of this bone. Usually birds have most of their beak made up of this bone, which is called the premaxilla. So it was a very unique adaptation in the Mesozoic for these birds. The birds are called enantiornithines. Again, they have nothing to do with the origin of modern birds. This is an artist's reconstruction of what falcaticale means, and I think I showed on the last slide that it means small scythe, in other words, for the shape of the beak. And this is very similar to what we see today in toucans and in this hornbill. But theoretically, I wasn't interested in any of that stuff. Of course, I'm fascinated with it. But I'm a mammalian paleontologist, so I was interested in going there to find early mammals and potentially even find the proto-lemurs or the proto-tenrecs or whatever. And the chances of doing that were pretty slim. This is the fossil record for the Mesozoic from the northern hemisphere. Each one of these dots represents like abundance or diversity. So from these big dots, there's a whole lot. From the little dots, there's not so much. What about for the southern hemisphere, for the Late Cretaceous? So this interval, the Late Cretaceous, is 35 million years long. And when we started in 1993, there were a couple of fragmentary jaws and some isolated teeth from Argentina, and over here, a few, like 5 or 6 isolated teeth from India. So what were the chances? I mean, I actually wrote a grant proposal stating that we were going to go there to find mammals. The chances were very, very slim. Go to Madagascar to find mammals. So despite that 2.5 day drive up to the bereaved area, and we got there in the middle of the night, pitched our tents, tired as anything, and woke up the next morning. We saw this outcrop about a quarter mile away. We ran over there because we were so excited to be there, forgot about breakfast and everything else. And within 20 minutes, this graduate student, now a professor at Duke University, said, "Dave, I think I found a mammal." I thought, yeah, right. And I didn't believe her, but she found the specimen right here. And this is the specimen. I looked at it. It's got all the characteristics of a mammal tooth. It's got more than one root. It's got a sharp boundary between the crown and the roots. And it's got complex morphology on it, and I knew it was a mammal. And I started jumping up and down and screaming. I was screaming in French, and I don't even speak French. It was just like one of those magical moments of discovery, and we were all just jumping up and down for joy. We were there for another 6 weeks. Guess how many more mammal specimens we found? 0. None. So of those 25,000 specimens that we have, and I'll show this in a second, we have, in fact, I'll show it right now. These are the specimens that we have, with the exception of 2 that I will elaborate on. So we've got, I think there's about 11 specimens here. This is one of them. So these are fragments of teeth, part of a vertebrate, part of a femur, not much at all relative to the 25,000 specimens that we have. So we were there for another 6 weeks, and we were finding all these dinosaur skeletons and croc skeletons and everything else, and that's what kept the project rolling along. But in 2010, so what now, 17 years after we started this project, we had a crew further out west, and they were really in a remote area, and they were tasked with collecting a whole bunch of fish fossils because we knew that there were fish in these beds and of the same formation but closer to shore. And so they made the prescient decision to basically take out huge chunks in plaster jackets and bring them back, and we brought them back into the lab. I was at my former place of employment, Stony Brook University, and we had access to CT scanners in the medical school. And so we scanned this thing, and it was filled with fish bones, but in this one corner was something else. And that something else was this. It was a mammal skull. And that is also up here for you to look at later. It's about that long. And mammals during the Mesozoic were all shrew and mouse sized, so to have a skull this big was highly unusual. This is actually the second or third largest Mesozoic mammal from that whole interval of time. And it's also bizarre. It has really weird teeth, which are not shown here. It's got these big flanges on the side of its face. This is an artist's reconstruction of what it might have looked like. But we also did micro-CT scanning of this. And this was in the early days of micro-CT scanning. The technician who worked on this put in 2,500 hours to segment this out so we could identify the individual bones. But the advantage of micro-CT scanning is that we can look inside. So we can look inside the nasal cavity, we can look inside the cranial cavity, we can look inside the inner ear, and be able to assess things that we couldn't before. So here is the brain case, or the brain, the actual brain, as reconstructed through micro-CTs, and it's really odd. For one thing, it's angled. It's not more or less horizontal like it is in most mammals. It's got this massive olfactory bulbs, in other words, sense of smell. And these are the largest olfactory bulbs relative to body size of any known mammal. Down here in green are the cranial nerves. Here are the semicircular canals, the organs of balance, and here's the cochlea. And from these, we know that it was a highly active animal. It had high frequency hearing, and as I said, a good sense of smell. So CT technology has really revolutionized what we do. It really allows us to breathe life into these animals and understand them much better. So this is the second of two mammals that I said I would describe. The other one is this. So this is like beyond my wildest dreams of what we would find there. We have a complete skeleton, and there's a reconstruction of it here as well as a 3D representation of it here. But this is the actual skeleton. Absolutely complete down to the tiny little sesamoid bones on the fingers and toes. Really a remarkable specimen. And we named it Crazy Beast. Adala in Malagasy language means crazy, and therium is a commonly used suffix for naming mammals. It means beast, so this is a crazy beast. Why do we think it's crazy? It might look like something like a badger and therefore not that unusual, but there are at least 30 what we call autapomorphies. In other words, totally unique features in this animal that make it seem really weird or bizarre or crazy. And so I'm just going to show you one. I mean, I'll mention one in passing, and the one in passing is that it's got more trunk vertebrae than any other known mammal, but it's also got really weird things like this intranasal vacuity. We have no idea what that was used for. There's no modern analogy to ping off of for that. But here we are with another kind of family tree. Don't get bogged down in it. Here are Vintena and Adalatherium. Here are the three modern groups of mammals, monotremes, marsupials, and over here, eutherian or placental mammals. And obviously, eutherian mammals are the ones that are found in Madagascar today. Vintena and Adalatherium are off doing their own thing. So again, we have failed to find ancestors of the lemurs or the tenrecs or whatever else lives in Madagascar today. So again, this is kind of a summary of the animals that we found, but we have to kind of put them into the context of the plate tectonic history of the southern part of the world. And so here there should be some familiar features. Here's Africa, South America, Antarctica, Australia. This is the Indian subcontinent annexed to Madagascar. And this is about 100 million years ago. Remember that the time period that we're looking at, finding animals in, is 67 million years, so way up here, and we'll get there. So at this time, India and Madagascar were together, and I've referred to this as Indo-Madagascar. And then by 83 million years ago, actually by about 88 million years ago, the schism between Madagascar and the Indian subcontinent happened, and then the Indian subcontinent took off on its own through the Indian Ocean and then crashed into Eurasia to form the Himalayan mountains. But the bottom line here is that at 88 million years ago, Madagascar was completely isolated in the Indian Ocean. So here we are at the time period at which we are finding fossils. And there they are, that whole array of fossils up at 67 million years ago. This is the time at which Madagascar became isolated. There's more than 20 million years. And I've, again, used the words weird, crazy, bizarre, everything else. But the point there is that there was 20 million years for them to adapt to their own environment and to become unusual relative to mainland animals. And they're not bizarre. They didn't think of themselves as bizarre. They were just adapting to their own environments. So getting back to that original question, the question was, how did these modern animals get to Madagascar, and when did they get there and from where? Unfortunately, we have no potential ancestors. We failed. But this is negative evidence. Why aren't those proto-ancestors there? Well, in the interim, since 1993, there's been a lot of work done on the modern animals and the modern mammals. I'm just using mammals as an example. I could talk about snakes or frogs or something else, but mammals are the best known. And so these are the 4 groups of modern terrestrial animals that live on Madagascar today, including, of course, this signature group, the lemurs. And so the molecular work, it takes DNA or RNA and is able to estimate divergence times. In other words, at what times did they evolve from other placental mammals to become lemurs, to become tenrecs, to become something other than their stem group, their stem placental group. And the bottom line is that for all of these 4 groups, the divergence times that are estimated are anywhere from as old as 60 million years ago up to 20 million years ago. There you have it. That's why we didn't find proto-lemurs and proto-tenrecs and anything else. They didn't exist at the time. So our negative evidence coordinates with what is known from molecular biology. And also, if we look at how this can possibly have happened, we need to know something about how those animals got to Madagascar. What were the directions of ocean currents? Well, most of the ocean currents today go from east to west across here, but there's been some paleocurrent modeling based on the Indian subcontinent and how that drifted through the Indian Ocean and disrupted circulation patterns. So here's a rough outline of Africa, and there's Madagascar. And you notice these lines are going from Africa to Madagascar. And so knowing that, and knowing that Madagascar has been in its place for 120 million years, in other words, it hasn't been moving out in the last 88 million years ago since it became separated from the Indian subcontinent. It's been where it is relative to Africa for much longer than that. And so we have to get animals from here, from Africa, to Madagascar. And what is this distance across the Mozambique Channel? The closest distance is about 240 miles. And you might think that that's impossible to traverse. I mean, how could that possibly happen? We know enough from modern day actual visual reports of huge rafts of vegetation during cyclones being ripped out of these East African rivers out into the Mozambique Channel and crossing towards Madagascar. And this is also true in South America, and a lot of the Caribbean islands have shown these rip-ups of mats of vegetation. When I talk about mats of vegetation, I'm not talking about a little dinghy-sized thing. I'm talking about huge ocean liner-sized mats of vegetation with standing trees on them. And yes, they slowly break apart. But over the course of 66 million years, the improbable becomes just a little bit more probable as time progresses. And so, as crazy as it might seem, this cartoon basically explains that that model of these animals related to their divergence times arriving on Madagascar. Notice that these are all small animals and that the large animals are not represented on Madagascar today. So just to try to get you to believe that that is even more possible, just this year there was an article published saying that looking at relationships of mammals, relationships of iguanas. This is the desert iguana of southern North America, off the coast of North America. This animal is in Fiji. These are close relatives of each other. And these authors speculated that the Fiji iguana originated from Western North America. And basically that means going approximately 8,000 kilometers across that distance. They backed that up with a bunch of other estimates, and here is the champion, which is that Fijian iguana. But if you look at all the animals down here, well, I'm taking a sip of coffee, you'll see that there are a lot of other island animals that have traversed a lot greater distance than the mammal groups from Madagascar. And so again, given enough time, the totally improbable becomes ever more probable, and that's the bottom line. So that's the current model. We can continue to test that by finding more fossils and doing more molecular analyses. But this is kind of the summary of the scientific discovery. Again, 32 years of scientific research. Through time, we know that Indo-Madagascar broke away from the rest of Gondwana about 120 million years ago, that Madagascar became isolated from the Indian subcontinent about 88 million years ago, and then during that time, the vertebrate animals that were isolated on Madagascar became, again, unique, bizarre, weird, and so on and so forth. But then this happened. The asteroid impact at about 66 million years ago, and there's no reason to think that things were different in Madagascar than they were in other parts of the world. It decimated the faunas, and so probably wiped out everything that you see here, all the lineages that you see here, and then after that, animals colonized slowly across the Mozambique Channel or even from the Indonesian side and evolved into the various groups. So that's that. I want to then kind of talk about very quickly science-adjacent matters. In other words, I was very ignorant, very naive about Madagascar. I've admitted that, and it's definitely true. So I had really no idea what to expect. And we were able to get into Madagascar in 1993, and it's a period during which this autocratic leader was not in power. But these three leaders are the main ones that have held sway since we've been working in Madagascar. So he was autocratic. This was a true democracy. He was overturned in a bloody coup by this fellow who is currently the president. He was very popular because he was a disc jockey. And anyway, that's one aspect. The other aspect I want to talk about is the whole atmosphere of neocolonialism. It's something we're very, very sensitive to, and in paleontology this has become very important and very appropriately important to discuss, and there are a number of papers that have been written about this in recent years, about taking fossils from foreign countries and bringing them back and doing the science on them, but not really involving local researchers. And so it goes on, but kind of summarized in this one paper by Riley Black, and she said paleontology often relies on researchers from North America and Western Europe building their reputations on fossils from other parts of the world. And I have to admit, we're guilty of doing that. We hit a mother lode, and many of our, me and my North American and European colleagues have built our reputations on that. But then this other part, without involving local researchers or giving back to local communities, I would like to plead not guilty on that, and I'd like to demonstrate what we've been doing and what we've done. And turning to legal matters, for instance, we are in full agreement with the Malagasy government and the University of Antananarivo in having collaboration agreements to work there. This is our most recent collaboration agreement with the Denver Museum and the University of Antananarivo and various branches of government. And that agreement basically says that all collected specimens can be exported for preparation. The reason for that is they don't have the facilities, nor do they have the training. We're trying to increase their level of training and facilities so that they can become totally independent into the future. And at the moment, all holotypes, these are basically the best specimens, the most complete specimens, and 1/2 of all other specimens must be returned to Madagascar upon completion of study. Sorry about my voice. It's just given out. So some rationalization for that comes from this paper. This paper basically documented that significant collections of natural history museums have been destroyed through a whole variety of things, natural and human-induced. 57 institutions across 30 countries have had their collections decimated. And the current state of security for collections in Madagascar, quite frankly, is not good. And so their solution, these authors suggested that the solution is simple, where possible, spread material out into more than one institution to avoid the loss because of any potential disaster. Every country is different. Every country has their own different rules, and every country has a different set of circumstances. For our purposes, we feel that this is the best solution for us, both for Madagascar and for us in the United States. And it states that leaving all specimens in Madagascar where they could not be collected and safely extracted from rock matrix yet, and again, this is where providing facilities and providing training is important, or returning all specimens after processing is too simple a solution, and in this case, ultimately counterproductive, both for Madagascar and for us. So we tried to build infrastructure in Madagascar, and that has come in the form of providing a collections facility. And this was funded through my former place of employment. And then we stocked that facility with 80 specimen cabinets from the DM&S when we converted over to the Avenir Collections Facility. And this is the collection facility in Madagascar today. We also built a classroom, a paleontology classroom, and this is that classroom. This was a big deal in Madagascar, and so this is on the donation day, and this is a plaque that involves the Prime Minister of the Republic. This is the Minister of Higher Education who gave a very fine speech dedicating that collection facility and classroom. We've also, as I've alluded to already, tried to train and collaborate with our colleagues in Madagascar, and this is taken many forms, pardon me. So we trained them in the field. We've trained them in collections management here at the DM&S as well as in the University of Antananarivo. We trained them in fossil preparations. And we've served on a number of graduate committees, and that's resulted in 7 master's theses and 4 Ph.D. dissertations. And we've interacted a lot. We've brought colleagues and graduate students here to the US for training as well. And so here's a bunch of slides just to demonstrate that. This is our field crew, and basically the takeaway here is that it's equal parts US and Malagasy colleagues. This is from 2015, along with a lot of the plaster jackets that we extracted. This is the most recent expedition in 2023 with Natalie, our chief preparator, and Pat O'Connor, our director of earth sciences. And this is just examples of training. This is Ray Rogers, our geologist from Macalester College, training both Malagasy and American students in the field. This is our star Malagasy graduate student, Bakuli Rakutazafi, here working in the Hell Creek Formation in North Dakota. And here's Bakuli and a professor from the University of Antananarivo, Hasana, being trained by our collections manager, Kristen McKenzie. And here's training in Madagascar. So we hold workshops on a number of different topics. Here's Pat O'Connor teaching about research methods, and here's our collections manager in charge of the Madagascar collection, Sierra Swenson, sitting in the back with a Broncos hat on. And here she is training in collections management. This is Sadie Sherman, one of our preparators, teaching Hasana and Bakuli aspects of fossil preparation. We've served on a lot of graduate student committees, and these are two of our fairly recent graduates, Leva, and here's Bakuli again with Pat serving as one of her mentors. And when we have Bakuli and Hasana in the United States, we've facilitated their ability to participate in conferences like the Geological Society of America, Society of Vertebrate Paleontology, and including a workshop here at the DMNS. And then finally, we've also worked with local communities, and this has taken on many different forms, but again, this was my ignorance. I didn't know how poor a country Madagascar was in terms of GDP relative to GDP per capita. It's the 7th poorest nation in the world. It doesn't have to be that way. It's very rich in natural resources, but people, especially in the countryside, are incredibly poor. A level of poverty, unless you've been to Madagascar or another similarly undeveloped country, you can't appreciate. And so these are some pictures of children. The children would follow us in those early years all over the place. We'd be walking tens of miles from camp. They'd be following us and giggling and laughing and pointing to us because they'd never seen people like us before. And we had things that they'd never seen before, things like pencils and pens and cameras. And then later on, we had picture books that we brought for them. And then later after that, laptop computers, and then finally handheld GPS units. And, as this was all going on, we'd ask them questions like, why aren't you in school? It's a Monday or it's Tuesday, whatever. And they said, we're not in school because there is no school. Bottom line is these people are every bit as intelligent as any of us, but they don't have an education. So nobody in the village, the main village that we worked in, adults or children could read or write. So that was kind of eye-opening to us. So this is a typical Malagasy house. It's the size of a kind of a small bedroom in an apartment or a house here. Mud floor, dirt floor, grass walls, grass roofs, maybe a tin door. These are children. These are from probably 1993. And very, very poor, virtually no clothes, and certainly no toys. They played with sticks and stones and each other, much more than our own kids do. Villagers were very helpful to us. They were always looking for employment. We would hire them to help us carry out dinosaur bones. I could tell a story about this, but I won't, this particular one, but for reasons of time. But they were very helpful. They showed us where dinosaur bones were. They helped carry things out. And so in 1996, I held a meeting with the villagers, and I basically asked the village elders, this is the chief of this tribe in this area, you've been very kind to us. What can we do to help you? And I didn't really know what to expect, but their first answer immediately was education. We want an education for our children, because they knew that was how to break the cycle of poverty. Well, back to this meeting, my next question was, well, how do we do that? And they said, well, you could hire a teacher. And we didn't really know what that would cost, so I asked how much it would cost. And the answer was $500 for a year. So we went back to our camp and we raised $500, gave it to them, and then went back to the US and hired that teacher. And that teacher, this isn't actually that teacher. That happened not during the time that we were in the field, so these are not my photographs, but I know that it was like this because they have big mango trees, and so school was held underneath the mango tree with a blackboard nailed to the tree. So this was just so eye-opening to me, and we decided to do something about it. So I started an organization called the Madagascar Ankisi Fund. Ankisi means children in the Malagasy language, and the purpose was to provide health care and education to these children. Why health care? Because I have kids of my own. At that time, they were very young, the same age as a lot of the kids that we played with there. And the kids were just like our kids. They'd crawl all over us and wrestle with us and play soccer with us and so on and so forth. And then we come back the next year and many of them weren't there. And they weren't there because they had died of easily treatable diseases. Respiratory infections, diarrheal disease is a big killer, malaria is a big killer. So I decided with not too much in terms of resources that we could do something about that. And so I started this fund. And this is the logo that was developed at the time. I had a son that in 8th grade, and the art teacher, I convinced her to do a logo contest. And this is the winning logo. It's not my son's. I love this logo because it takes the Malagasy flag, colors of the Malagasy flag, and puts it into a rainbow to unite our paleontological project with building schools and so on and so forth. The only downside of this is that it looks like our predatory dinosaur is about to eat those little kids. Can't have everything. Anyway, what have we done? We built 6 schools. 5 of them are primary schools. 1 is a secondary school, and we've renovated an orphanage. These are the 6 schools built at different times. We now have about 1,000 children that we serve in this way. The kids are super eager to learn. Class size is much larger than it is in Colorado, roughly on average 50 kids per classroom. This is the first school that we built. When we started it, actually if you go back here, this is the start of that school right here. There are about 30 kids. Now there are 192. And so we've had to expand this school and most of the other schools that we built. I don't have a formal survey. I've got an informal survey. And that is that fairly early on, I went to visit this little girl's parents. Her name is Naridra. And her parents were friends of ours. And I usually have something in my pockets for the kids. And this day I had a piece of chalk, and she said, "Stop, I want to show you what I've learned in school." And she goes to the side of their house. They were actually quite wealthy because they had tin on the side of their house. And she writes out sentences in French and doing some arithmetic. There's one arithmetic mistake in there, but don't worry about that. But the bottom line is she had learned a lot. And then many years later, I came back and found her again. This is Naridra, the same little girl. Here she is with 2 of her own kids. This is her dad, Boniface, who I know very well. And she is now an accountant. And she is supporting her immediate family and her extended family as well. How have we done this? At least on Long Island, where Stony Brook University was, I had a good relationship with a lot of schools. I haven't been able to build that here in Denver yet. But I would do assemblies and tell I've got the perfect hook, right? I've got dinosaurs. But it's really amazing how kids are entranced with other kids that live differently than they do. And so I got these various school groups to do small fundraisers, anything from, bake sales to readathons to walkathons and whatever. And I love the concept of kids helping kids. And it was mutually beneficial because the kids on Long Island really got to learn a lot about Madagascar, but they also really learned that they can make a difference in the world. And one of the things that we've done is developed pen pal associations between American kids and Malagasy kids. Again, learning about each other has been fascinating on both sides. And we've, the higher achieving students, the ones that still want to go to school after going to primary and secondary school, we've supported to go to the nearest city. We provide room, board, counseling, chaperones, so on and so forth, to go to high school and university. And now in a village where nobody could read and write when we first got there, there are kids who have actually graduated from university. And it's not a university like our universities, but it's a university where they really learn some practical things that they can do. And these are some of the high school students in one of the villages. And we've supported some of those university graduates to and encouraged them to develop sustainable ventures. And in that regard, I'm going to highlight three of our graduates, Yvonne, Armand, and Germaine. Yvonne is now a paramedic and a midwife in the village, and has probably saved many lives. Armand is an agronomy expert, and he actually started a women's permaculture association. And Germaine was primarily an aquaculture expert, and he has just recently started a fish farm. And fish farms are incredibly important because it's a source of protein that is so lacking. So this is the Women's Permaculture Association. I'm seeing the clock. I need to wrap this up. And this is planting and supplying water. This is harvest time, a rich supply of peanuts. This is Germaine and his fish farm. Just finished the first year of that, and it was incredibly successful. Lessons learned along the way, so the second year will be much more beneficial. And then also related to healthcare, we've provided monthly medical clinics and annual dental clinics. Excuse me. And this is why protein deficiency is rampant. These kids are suffering from kwashiorkor, which is protein deficiency. Dental disease is rampant, so are skin diseases. And so we set up clinics in the schools. We convert them into clinics on an off day. And the villagers in Madagascar don't have cars or trucks or not even bicycles. Sometimes they have ox carts, but mostly they get around by walking. And we put out notices weeks in advance, and the women and the mothers and grandmothers would walk for literally hours, maybe even days, to bring their children to these clinics. And these are three of our Malagasy doctors holding clinics once a month. These are dental clinics from Stony Brook University. These are students who have finished all but their final year, and they're expert in certain procedures, including extractions. And they basically do a world of good because dental decay can become systemic and can kill. And so I literally think that these dental teams have saved many, many lives. We don't request any payment, of course, because they don't have any money, but they're always so grateful, and so they give us things like baskets as well as chickens as a thank you for the work that these dental teams did. And then finally, the most important thing we can do for healthcare is provide drinkable water, and we've done that for about 24,000 villages. Again, these aren't my pictures, but they could be. They're off the internet. But what we've done is we've dug wells with the support of Rotary International, and that's been useful. But still, if you have been drinking out of a stream next to your house or a quarter mile away from your house, you're not going to walk a quarter mile away to or more to go to a well if your family has been drinking out of that same stream for generations, and if you know nothing about microorganisms and what they can do. And so we came up with a different solution, which is basically using UV radiation by putting clear bottles up. And this is a method that has been used in Latin America a lot. Putting clear bottles at an angle to the sun, and then that gets rid of 99%, something like that, of the coliform bacteria, and virtually eliminates diarrheal disease for the kids in the area. So this is just one example on one house. And it's effective in cutting diarrheal disease in half, less than half, for children under 5. And then my, again, informal example is this little boy over here. This little boy was deathly ill. And within 3 weeks of drinking good water, he became a very healthy young fellow. So I think I'm going to end there. Again, I have to underscore 1,000 times that this is not a one-person show. There's been so many people involved in this, so many institutions involved in this project over the course of 32 years. And I can't thank them enough. And I'll turn it over to questions, except for I have to acknowledge these two gentlemen. These two gentlemen are the men on the ground doing the work for the Ankizi Fund, Radu and Jonah. And I will take any questions, but I have one question for you before I go. What's the right answer? Well, C, you got it. Right. You were awake. Great.
Let's give a round of applause to Dr. David Krause. If you need to head out, please exit the way you came, but instead of entering or exiting through the west doors, we're going to ask you that you exit through the museum. And if you wander, that's okay. You're not going to get an extra look from me, but we ask that you exit through the north doors towards the parking lot. With that being said, Q&A is now ready. Paula, I saw your hand, but I'm going to go to the public first. And also, speaking into the cube is an accessibility need, so I ask that you all do speak into the cube. Thank you. Do you mind passing that to him?
Thanks for a great talk. I was a little surprised that you're able to find protein that could actually be sequenced in a Cretaceous bird fossil. Have you ever been lucky enough to find DNA?
No, we have not. And again, this is nothing that I did personally, but this kind of fibrous protein, I guess, is identifiable as either alpha keratin or beta keratin, and the analyses were good enough to do that, but not to get to the DNA stage.
If you want to pass it back, you're more than welcome.
Put your hand up again.
I think this.
There.
Hi, I know nothing about paleontology, so that'll become apparent with my question. Why, you said there were no fossils from first 60 million years, but I didn't understand why.
Yeah, and I didn't explain why, so I'm not surprised. And I think I have a slide to that. No, I don't. The bottom line is that Madagascar has a lot of topography, so a lot of it is highlands, and it's only on the west coast that you have deposition. In other words, erosion from the highlands into these lower areas that got deposited. And those lowland areas filled up over time. It's called accommodation in geological terms. And so it filled up during the Permian, the Triassic, and the Cretaceous. And then it totally filled up to the top. So after that time, later sediments, after 67 million years ago, yeah, you got it right there, they got washed out into the sea. And so those tertiary sediments from today back to 67 million years ago got washed out to sea and didn't get deposited, and therefore fossils weren't deposited at the same time.
So is it the currents on the east side that mean that's the reason there's nothing on the east side?
So the east side is, the east side has much higher topography than the west. So anything there gets washed out to sea even quicker than on the west side. There's no lowland areas on the east side. It's all high elevation rainforest.
So why, you said you would answer this if we asked, why do you think the early expeditions did not discover more intact fossil specimens?
Thank you for that question. So the reason we have such good preservation is because these fossils were deposited in debris flows. And debris flows are basically like flash floods, except with a lot of sediment in them, kind of like milkshake consistency. And back in the Cretaceous, just like today, there were 9-10 months of extreme drought, and then the rainy season for 2 or 3 months. And during those rainy seasons is when these flash floods or debris flows would come down. So putting yourself back into the late Cretaceous, if you were a dinosaur that died 2 days after the rainy season, you're going to be sitting out in the dry season for 10 months. And your bones are going to get scavenged, they're going to get chewed up, they're going to get bleached out, they're going to turn to junk. If you were an animal that died a week before the debris flow, or even in the debris flow, there's a good chance that your bones will be well preserved. So that's part of the explanation, but the real answer to your question is that all of these bones